in this lecture we will see Fourier inversion and Plancherel theorem. Okay. So let's start. I'll start with the statement. But before we write down, let's recall what happens in let's say Hilbert space. If I have a Hilbert space, well, we'll have a orthonormal basis, right? So separable Hilbert space. Let's call that Ej, I equal to 1 to infinity, right? So if I take a vector in the Hilbert space, well, I know how to write it, right? So you take the coefficients like this, right, and you can get back your vector by adding these things, right. Now this is like the Fourier coefficient or the Fourier transform. Okay, so if you recall the definition of the Fourier transform, it is f inner product with an exponential. Okay, and to get back your function, you sort of add up all those Fourier coefficients with the exponentials, right. So here we have an integral, so instead of summation, we will have an integral. Okay, so that is how the Fourier inversion would look like. So, but being an integral, there are certain technical conditions that will come in. So let's say Fourier inversion, let f belong to L1 of Rn. Suppose f hat also belongs to L1 of Rn. Okay, so that is already a condition, right? So we saw an example chi minus 1 1 whose Fourier transform is not in L1. Okay, so it can happen that it is not in L1, but suppose the Fourier transform is also in L1, then you can invert. Okay, then f of x, so you can recover f from f hat. So f of x is, so remember the 1 by root 2 pi to the n, there is always, okay, f hat t, right, e to the, so in the definition of the Fourier transform it is e to the minus I x t. So here you will have I x dot t dt, right, t is the Fourier transform variable. Okay, so notice the difference here. It is, if you start with e to the minus I x t in the definition of the Fourier transform, here it would be e to the I x t. In the Fourier transform, if you start with e to the I x t, here you will have a minus, and there is a 1 by root 2 pi to the n. If you put the 2 pi here, then this will not be there. Okay, so that's these are all sort of easy to deduce one from the other. If you prove this, you can prove whether you put a 2 pi here or not. That's just a dilation. So you know how Fourier transform behaves with respect to dilation. Well, this equality is true almost everywhere. Okay, so all the points in the statement is very important. It's almost everywhere. Why? Well, so notice that f hat is in L1. So this function, so forget f for the time being, this function as a function of x is continuous, right. It's exactly like how you prove Fourier transform is continuous, right. If xn converges to x, e to the I xn dot t will converge to e to the I x dot t. F hat is in L1, so it's bounded by f hat which is in L1. So dct will tell me that this integral converges to the corresponding integral. So this function as a function of x is continuous. Of course, f is only in L1, right. So there are points where things can go wrong. So this is an equality almost everywhere. Also, this function agrees with a continuous function almost everywhere. You see, so this is a rather strong condition to have. But if you have that strong condition, you have inversion. Okay, you can get back your function from the Fourier transform. So that's for the first point in this lecture. So we'll prove this. Proof is not very difficult, and you already know one instance of the inversion. So that is for the Gaussian. Okay, so recall that P0 of x is equal to e to the minus x square by 2, and phi0 hat, the Fourier transform is phi0 itself, right. So you know that phi0 is an eigenfunction for the Fourier transform. Okay, so we'll use this guy. So, let us start with one integral. So, let us put 1 by root 2 pi to the n integral over Rn f of f hat t. Okay. So, let me write e to the I x t here, x dot t dt. Okay. The fact that phi 0 hat is equal to phi 0 is essentially, this is Fourier inversion for the function phi 0. So, that is trivial. Okay. For Gaussian, this theorem is trivial, because if I put the Gaussian here, with respect to t, it's an even function. So, putting a minus t or plus t does not matter. So, that is simply the Fourier transform again, and Fourier transform of that is Gaussian we have already computed. So, Fourier inversion is sort of a trivial statement for the Gaussian, and we will use that to prove it for all functions. Okay. So, we start with this integral. This exists because it is a function in L1. So, this is a very nice function, right? It is a continuous function vanishing at infinity, just like the Fourier transform. Well, I am going to put a summability factor here. So, we will call that phi 0 of epsilon t. Okay. So, epsilon is some positive constant. Now, well, this is equal to, I am going to plug in the definition of the Fourier transform here. Okay. So, I will have 1 by root 2 pi n integral over Rn, and the Fourier transform I have another 1 by root 2 pi to the n integral over Rn f of x e to the minus I x dot t dx, right. So, this much is simply the Fourier transform of f, right. So, I have not done anything except writing down the definition phi 0 of epsilon t e to the I x dot t dt. So, let us be careful, there is an x here, right. So, let me change this to y, so that there is no confusion. Okay. So, this is the Fourier transform of f at the point t, right, f y e to the minus y dot t dy. X is a fixed point, right, x is in Rn, and I am trying to invert the Fourier transform at the point x, okay, and I want to get f of x. So, now because of this extra phi 0 epsilon t, the t integral is fine. Remember, this is the Gaussian, right. So, you put an epsilon here, you will get e to the minus epsilon square t square by 2, but it still has exponential decay. Okay. So, t integral is finite, y integral is finite, because f is in L1, right. So, let us look at the modulus of this. This goes away, this goes away. I have phi 0 and f, but f is in y, phi 0 is in t. So, both the integrals are finite, right. So, this means by Fubini's theorem I can interchange integrals, alright. So, interchange integrals, well, I integrate with respect to t first and f second, okay. So, I have integral over, so 1 by root 2 pi to the n, integral over Rn, f of y and dy, right. So, I have taken the dy integral outside, I put the dt integral inside. So, that is 1 by root 2 pi integral over Rn. Well, what are the things I have? I have phi 0 of epsilon t, right, and I have exponential. So, e to the I x dot t e to the minus y I y dot t. So, that is e to the I x minus y dot t, okay, dt. Right, all I have done is interchanging integrals. But phi 0 is a nice guy, right, this is our Gaussian, and this is simply calculating the Fourier transform at x minus y, right, of this dilated Gaussian. So, remember how f delta x, and you take the Fourier transform, you will get 1 by delta to the n f hat at t by delta, right. So, because of this epsilon, you will get a 1 by epsilon to the n phi 0 hat at x minus y by epsilon, okay. So, this becomes 1 by epsilon to the n phi 0 hat at x minus y by epsilon, right, because of that epsilon. But now this looks familiar to you, right? Phi 0 hat is phi 0 itself, which is the Gaussian. So I'll just forget the hat. So what is this now in our language? Well, there is a 1 by root 2 pi to the n Fy 1 by epsilon to the n phi 0, forget the hat because phi 0 hat is phi 0 itself, x minus y by epsilon. So this is dilation of phi 0 by epsilon convolved with f, right, x minus y. So this is f convolved with, remember we redefined convolution using 1 by root 2 pi, right. So this is f convolved with phi 0 dilated epsilon at the point x. Right. Remember phi sub epsilon was 1 by epsilon to the n phi of x by epsilon, right. So that is precisely what this is. So in all this, if you look at it carefully, all that you have used is phi 0 hat is phi 0, there is nothing else we are using, okay. That's really interesting about this proof. Okay, so now let us look at both sides again. So I am assuming that the Fourier transform is in L1, okay. Let us look at this portion as epsilon goes to 0. Well, what will happen to this as epsilon goes to 0? Remember phi 0 is the Gaussian, so I have e to the minus epsilon square x square by 2. As epsilon goes to 0, that guy goes to 1. So this goes to 1 and it's bounded by 1, right. Whole this is bounded by 1. F hat is a function which is in L1. So by dct, this will go to f hat t e to the ix dot t dt, precisely what we want, right. So this as epsilon goes to 0 by dct converges to 1 by root 2 pi to the n integral over Rn f hat t e to the ix dot t dt, right. That is the left hand side. This happens for every x, right. Whatever x is, this is going to happen, right, because e to the ixt still has modulus 1, so it does not change. So this converges pointwise for each x, this function of x as epsilon goes to 0 will converge to this function of x. What happens to the right hand side? Remember phi 0 is a nice function e to the minus x square by 2, it is in L1, its integral divided by root 2 pi n will be 1, right. So if I dilate that, I am going to get an approximate identity, right. So this will converge as epsilon goes to 0, f is in L1, so the convergence is happening in L1 to f of x in L1 of Rn, okay. So it is not a pointwise convergence, it is an L1 convergence, f convolved with phi 0 sub epsilon converges to f in L1 of Rn, okay. So now you apply the usual measure theoretic argument. I have a pointwise convergence sequence, the same sequence converges in L1, so they will have to be equal almost everywhere, right, because there is a subsequence here which converges almost everywhere. So this function and this function will have to be equal almost everywhere, that is the inversion, right. So hence 1 by root 2 pi to the n integral over Rn f hat t e to the ix dot t dt is equal to f of x almost everywhere. So that is the Fourier inversion. So let us say corollaries, there are interesting corollaries. First is the uniqueness of the Fourier transform. Uniqueness, if f is in L1 of Rn and f hat is identically 0, then f is identically 0, right. So it follows from applying the inversion, because if f is in L1 and f hat is 0, that it is in L1, right, then you can recover f from f hat by this formula. but f hat is 0, so this is 0, which means f is 0 almost everywhere. Okay. So, it is a uniqueness, right. So, if I have two functions whose Fourier transform is same like f and g, then you look at f minus g will have Fourier transform 0, so f equal to g, right. So, this also tells me that f hat equal to g hat implies f equal to g, right. So, that is a uniqueness. Of course, all of them should be in L1, okay. So, as of now all of them should be in L1. It is true in general with various other function spaces, but as of now we can prove only when they are in L1. Okay, so, take two functions in L1 whose Fourier transforms are same, they will have to be same functions. Okay, second one is a technical corollary which we will use in the Plancherel theorem. Let f belong to L1 of Rn, f continuous at the point 0, okay, or 0 is a Lebesgue point, even that is fine, continuous at the point 0. If f hat, so f hat makes sense, right, f hat, f is in L1 of Rn, f hat would be a continuous function vanishing at infinity. But in general it can be a complex valued function because you have an e to the I x dot t in the definition, right. So, assume that it is a positive function, Fourier transform is positive, then then you can conclude that the Fourier transform is actually is integrable, it is in L1, and so you have inversion, right, and f0 would be 1 by root 2 pi to the n integral over Rn f hat t dt, right. The Fourier the inversion at 0 is true in the sense that f0 makes sense because it's continuous at 0. So, there is a well defined value for f0, and f hat, one of the conclusions is that is in L1, it is a positive function, so its integral is. So, look at the proof of the inversion. I want to prove this at 0, right. So, I am trying to say that f0 is given by something. What we have is something which is equal almost everywhere, right. I want to say it is true at the point 0. So, if you go through the proof at the point 0, so that means here there is no exponential, it is just f hat t phi 0 t, that of course converges by dct to the integral, that is fine. But if I look at this, I am going to get f convolved with phi 0 sub epsilon at 0. But 0 being a continuity point of f is a Lebesgue point, and remember the technical result we wrote down in the last lecture. If I have an approximate identity whose radial majorand is in L1, then I have f convolved with phi epsilon at x converging to f of x at all Lebesgue points. Phi 0 is a radial function which is decreasing, so its radial majorand is itself. Okay. So, for that particular phi 0 this works. So, f convolved with phi epsilon phi 0 at epsilon at 0 will converge to f of x, right. But f hat is positive, right. So, what we are saying is integral of f hat is actually f at 0. So, it is finite, right, or you can use Fathou's lemma. Okay. So, this is, so use the result f convolved with phi epsilon phi 0 epsilon at 0 converges to f0 because 0 is a Lebesgue point. Okay, along with the fact that Fourier transform is positive. Okay, so what we have just done is the Fourier inversion. So, if I have the function f in L1 and f hat is in L1, I can invert, right, I can invert and get back my original function. Okay. So, taking the Fourier transform you can see as some sort of decomposition, and inversion is putting together these pieces, right. So, f hat you put together with exponential, you will get f back. Okay. So, the next one is Plancherel. So, Plancherel theorem. Okay, let me state it and then we will Fourier transform. Okay, let us call this, give it a name, script f, okay, defined initially on L1 intersection L2 of Rn extends to a unitary operator on L2. Okay. So, in other words, script f would be from L2 of Rn. So, it is like extends, okay, L2 of Rn. So, this would be 1 1 onto isometry, right. So, okay, L2 norm is same as script f L2 norm, okay, which is what we denote by the Fourier transform. So, script f is simply a name for the Fourier transform, okay. So, we use the script f symbol to denote the Fourier transform, okay. So, this is something you have seen in Fourier series, right. The L2 norm of the function is the L2 norm of the Fourier coefficients, right. So, this is the continuous analog of that, but there are certain technicalities here, because if I take an L2 function, I cannot define the Fourier transform by the integral, because the integral need not exist, right. I need it to be in L1. So, that is why one starts with L1 intersection L2 or some other dense class. So, remember the class L1 intersection L2 contains all CC infinity functions, for example, or Schwartz class functions, for example, and so they will be dense in L2 or in any other LP, right. The definition of the Fourier transform which we started with makes sense on L1 intersection L2, because it is contained in L1. But think of it as a subset or subspace of L2. The theorem says that it extends, that definition extends to a unitary operator on L2, but it is not. So, if I take an arbitrary function in L2, it is not defined using the integral, okay, but there is a relation and you get a unitary operator. So, it is a 1 1 onto isometry, which is so the norm of the function and the norm of the Fourier transform are same. So, well, the proof of this is slightly involved, it is slightly more than what is there in the inversion proof, but we will use the inversion, okay. So, take a function in L1 intersection L2. So, here there is no problem, we can define the Fourier transform by the integral itself. Let us define f tilde of x to be f of minus x bar. Okay. So, this is also of course in L1 intersection L2, right. We are not doing anything too complicated here. F of minus x is also in L1 intersection L2. Taking the complex conjugate does not change the modulus. Let G equal to f convolve with f tilde. Okay. So, I am creating a new function out of f and f tilde simply by convolving. Well, what all can you say about G? G is going to be a very nice function. First of all, convolution makes sense, because f is in L1, f tilde is in L1, convolution makes sense. Well, f is in L2, f tilde is in L2, you can still convolve, you will get a bounded function. Well, once more, f is in L2, f tilde is in L2, convolution will be a continuous function vanishing at infinity. Remember one of the exercises, LP convolved with LQ, where q is such that 1 by p plus 1 by q equal to 1. Here it is 2. So, 1 by 2 plus 1 by 2 equal to 1. Then when you convolve them, you get a continuous function vanishing at infinity. Okay. So, it is, and both are in L1. So, when you convolve, you are still in L1. Okay. So, it has all kind of properties. So, this belongs to L1 first of all, and it also belongs to C0 of Rn. Okay. So, it is a very nice function. Okay. Let us compute the Fourier transform of G. Okay. So, G hat of T, well, what is the Fourier transform of a convolution? Under convolution, Fourier transform becomes the product, we have seen that. Okay. So, G hat T is f hat T times f tilde hat T, right. So, I need to know what is f tilde hat T. So, let us see that f tilde hat T. So, this is a simple computation. Hat T by definition is 1 by root 2 pi to the n integral over Rn f tilde x, right, f tilde x is f of minus x whole bar, right. So, that is f tilde x e to the minus I x dot t dx, right. This is the definition of the Fourier transform. Okay. Well, what is this? So, I want to write this in terms of the Fourier transform of f, right. So, change variables. So, the minus x, so here I will put x, so here I put a minus x, this goes away, fine. I have a bar, I take it outside, so I will need a minus here again, okay. So, I put a minus here and then bar outside, okay. So, that is simply the Fourier transform of f and taking the complex conjugate. So, this is simply f hat t whole bar. So, I simply changed the variable and took the complex conjugate outside. So, now g hat t looks very nice. So, g hat t is f hat t times f tilde hat t, but f tilde hat is the complex conjugate of f hat. So, this is simply f hat t whole square, right, which is positive. So, remember one of the corollaries we had, if I have a function whose Fourier transform is positive, something or the other happens, right. So, g is f convolved with f tilde, which is a very nice function. It is a continuous function, in particular 0 is a Lebesgue point, and g hat is positive. So, the corollary tells me that g hat is in L1, right. So, by the corollary, g hat will be in L1, right, because it is positive and g has continuity at 0, right. So, g will be in L1. Okay, so, that was the second corollary if you remember. So, now I have a function which is in L1 whose Fourier transform is also in L1. So, I can invert, right, and remember the inversion would be true at all points. Why? Because I have continuity. Remember you had two functions which are equal almost everywhere, but now g is continuous, g hat is in L1. So, when I invert, the integral is continuous. So, they will have to be equal almost everywhere, right. So, this implies by inversion g of x equal to 1 by root 2 pi to the n integral over Rn g hat t e to the I x dx dot t dt, right. This is true for every x, remember, because both sides are continuous. Both sides are continuous in x, okay, right. As a function of x, this is continuous, right. This is like the Fourier transform of an L1 function. So, you know it is continuous. G is continuous because it is a convolution. So, if they are equal almost everywhere, they will be equal for all points, right, because they are continuous. So, you can put any point. So, put x equal to 0, put x equal to 0 to get, well, what will you get? G0 equal to, so g of 0 equal to 1 by root 2 pi to the n integral over Rn g hat t dt, right, x equal to 0, right. So, e to the I x dot t becomes 1. So, let us write down both sides. G hat t we have computed, that is mod f hat t square. Let us compute g0, right. So, what is g0? g0 is f convolved with f tilde at 0, okay. Let us write it down. Remember, now the convolution has a 1 by root 2 pi to the n integral over Rn f of x minus y, right. So, that is 0 minus y f tilde at y dy. It is the definition of the convolution, right. F at x minus y f tilde y dy, x is 0. So, it is just f at 0 minus y f tilde at y. But what is f tilde at y? The definition of f tilde is f of minus x bar, right. So, that is f of minus y bar, okay. So, I have f of minus y here, f of minus y bar here. So, I will get mod f minus y square. Minus y does not matter because Lebesgue measure is invariant under x going to minus x. So, this is simply 1 by root 2 pi to the n integral over Rn mod f y square dy. Right. So, G0 is actually the L2 norm of f, right, multiplied by 1 by root 2 pi. So, now let us use this. Okay, so, I have computed G0 for you, and here G hat t is simply f hat t square. So, we get 1 by root 2 pi to the n integral over Rn mod f y square dy is equal to 1 by root 2 pi to the n integral over Rn g hat t is mod f hat t square dt. Right. So, what is the upshot of all this? So, we constructed f convolved with f tilde, used the Fourier inversion to get this, right. So, 2 pi you can forget. This tells me that the L2 norm of the function is same as the L2 norm of the Fourier transform, which means it is an isometry, right. But we started with L1 intersection L2, not for arbitrary function, but I have an isometry which is a bounded operator on a dense subspace. So, it extends to an isometry, right. So, now I will change to script f from L1 intersection L2 of Rn, right, that is where we define 2. So, this tells me that I land in L2, right, because this is finite. So, I go to L2 of Rn is an isometry. Okay. So, this by general function analysis results, because this is a dense subspace in L2, it will extend to an isometry, right. Hence, script f extends to an isometry. So, it is still slightly far away from the theorem, to an isometry on all of L2, right. Okay. So, script f becomes a map now from L2 of Rn to L2 of Rn, okay, with the property that script f L2 norm is same as L2 norm of f. Okay. So, that is what we mean by an isometry. Of course, it is unitary would mean isometry onto, right. So, we have to prove that the range is the whole space. Okay. So, the extension is something which you should keep in mind. We started with the dense subspace, proved that it is an isometry, and so it extends to an isometry on the whole space. Well, how do you define this on the whole space? I take an arbitrary function here. Since this is dense, there is a sequence of functions from here which will converge to that function in L2. And for those functions, I know how to define the Fourier transform. So, that gives me a sequence in L2. But because it is an isometry and here you have convergence, this would be Cauchy, right. So, it will have a limit, and that is your Fourier transform. Okay. So, it is defined in the functional analytic way by taking limits. For only functions of this class, I can write down the integral because it is in L1. Okay. So, you have to keep that in mind. If I take an arbitrary L2 function, I will be approximating it by functions from here and taking the limit of the Fourier transforms in L2. That is how it is defined. Okay. So, we need to complete the proof. So, here it is an isometry in L1 intersection L2. I have extended it to L2. Now, I need to show that it is a unitary operator, which means that the image is all of L2, right. But it is an isometry. So, image will be closed. So, it is enough to prove that I have a dense class here which is in the range of script f, right. So, to prove that f is unitary, we will show that the range of f is dense, okay, is dense. Okay. For that we use the Schwarz space. So, we call S of Rn. So, this was the collection of C infinity functions, right, which were rapidly decreasing. So, you multiply with any polynomial, differentiate f any times you want, that was in L infinity, right. So, this was my Schwarz laws. So, we use the Schwarz laws to prove that the range of script f is dense, in the sense that we will prove that anything in the Schwarz class is the Fourier transform of a function in L1 intersection L2. Okay. How do we do this? So, let us start with one way. So, claim is that claim f maps well, okay, let us start with this claim f maps Schwarz space on Rn to Schwarz space of Rn. In fact, it is 1 1 on 2. Okay, so in a 1 1 on 2 fashion, 1 1 on 2 manner. Okay, so that is a claim. And if we can prove this claim, then we are done, right. Script f is the Fourier transform, that is well defined on the Schwarz space, right, because Schwarz space consists of functions which are rapidly decreasing. So, they are in L1, they are in L2, they are everywhere. And on L1 intersection L2, we have a nice definition in terms of integrals. Okay. So, on the Schwarz space, we have the usual definition of the Fourier transform. And if we prove that everything in the Schwarz space is the Fourier transform of some other function in the Schwarz space, then when I look at the range of script f in L2, Schwarz space sits inside here as a dense subspace. Its image will have Schwarz space, right, because anything in the Schwarz space comes from the Schwarz space. So, image will have Schwarz space, but that is dense. Image is closed because it is a isometry, so it has to be onto. Fine. So, all that I have to do is to prove that everything in the Schwarz space comes from a function in the Schwarz space via Fourier transform. Okay. So, let us see what it does. So, let us start with some function in the Schwarz space and let us see what happens to its Fourier transform. Okay. So, f hat t equal to 1 by root 2 pi to the n integral over Rn f of x e to the minus I x dot t dx, right. Now, we are looking at the Fourier transform. I am starting with a function in the Schwarz space. What is Schwarz space? Schwarz space has the property that it has both smoothness and decay, right. So, remember the Fourier transform intertwines smoothness and decay, but this is a class which has both. So, any function here you take and take the Fourier transform, that should have both the properties, right, because smoothness will go to decay, decay goes to smoothness, and I put together both here. So, its Fourier transform should have both the properties, that is why it goes to Schwarz space itself. Let us see why by looking at this. So, I need to differentiate this as many times as I want, multiply it with a polynomial and see that whatever I get here is a bounded function, right. This is all I have to do. Okay. So, let us do that. Let us multiply, let us differentiate this first f hat and multiply by some polynomial, right. Remember, all these are multi-indexed alpha 1, alpha 2, etc. alpha n, beta is beta 1, beta 2, beta n, so on. Okay.
To prove that the image space, that means the range will be dense.
Yeah.
For that, you will prove this is 1 1 on 2 and so on.
Well, oneness we already know, right, uniqueness of the Fourier transform. So, ontoness, so if I take any any function here, it comes from some function here via Fourier transform, right. So, then everything here will be in the image of the Fourier transform on L2 and so it is dense, right. But this is going the other way. So, I am taking a function here and I am saying that we will land here, and similarly I will take one here inverted and say that I land here, okay. But there is still one catch, but we will do that at the end. So, let us see what happens to derivative of this multiplied by a polynomial. Well, how can you take the derivative? Well, because function decays fast, right. So, Fourier transform is differentiable, that is what we did. So, it is differentiable. So, when I differentiate this with respect to t, the derivative actually falls here. Of course, you have to take the derivative inside, that requires dct, right. So, you use dct, d alpha will come here. but when I remember I am differentiating with respect to t. So, when I put a d alpha here, I will get x to the alpha downstairs, right. So, x to the alpha is x1 to the alpha 1, x2 to the alpha 2, etc., and there is an I does not do anything, but that is just multiplying f with a polynomial, but that is a nice function, right, because f is Schwartz class. So, everything will make sense. Now, when I multiply by t to the beta, remember multiplication goes to derivative, right. So, this would be the derivative of x to the beta times x to the alpha times f, but that is also a Schwartz class function. So, we have no problem. Okay. So, let us do this let us do this one step at a time. So, let us start with derivatives first. So, d alpha f hat would be 1 by root 2 pi to the n integral over Rn fx d alpha of e to the minus I x dot t dx, right. That is simply dct, which is equal to 1 by root 2 pi to the n integral over Rn. If I differentiate this d alpha times, I get minus x to the alpha. So, minus I x to the alpha f of x. So, that is my new function now, e to the minus I x dot dx, right. So, that much is trivial. The only thing to be justified is how d alpha, the derivative goes inside the integral, but that is just dct. Okay. So, we are very close to the end. Let's multiply this with t to the beta now. So, if I look at t to the beta times d alpha of f hat at t, this is nothing but 1 by root 2 pi to the n integral over Rn. I have minus I x to the alpha f of x, right. This is my function. Then there is a t to the beta. Well, what is t to the beta times e to the minus I x dot t? Well, you differentiate that this guy beta times, you will get t to the beta, right. You differentiate this with respect to x beta times, you will get t to the beta. Remember, if I put a d by d1 with respect to x, I will get a t1. Similarly, if I take alpha 1, alpha 2, alpha n, etc., put d alpha with respect to x, I will get a t to the alpha. Okay. So, this I can write as with respect to x, okay, the partial derivative with respect to x beta times e to the minus I x dot t, right. Well, each time I differentiate, I get a minus I also. Okay. So, I should, strictly speaking, I should divide it by minus I to the beta. Okay. These are concepts which do not create any trouble for us. Dx. Okay. So, this much is simply dct, there is nothing, right. But I want to say that this is bounded, right. Well, so I want to write it as Fourier transform of something. Well, all the derivatives here will go to the other side by integration by parts. So, remember that is what we did first, right. So, if I had d1 with respect to x, then I can put it here. Remember, the n terms go to 0 because f is in Schwartz class. So, it vanishes at infinity, right, just like CC infinity. So, I can put it here and there is no boundary term. Okay. So, this would be maybe plus or minus. Okay. So, there is a, you do it beta times, you will get minus 1 to the beta, strictly speaking. So, minus 1 to the beta, these are constants which we do not have to bother about. 1 by root 2 pi to the n, okay, integral over Rn. All the derivatives will fall here. Okay. So, this is, but with respect to x, okay, beta of minus I x to the alpha f of x, okay, times e to the minus I x dot t dx. Okay. So, advantage is that this is the Fourier transform of something. Okay. So, if you look at this and call this capital F, this is some constant times capital F hat at t. Okay. A few more lines to complete the proof. So, whatever we have just proved is only partial of what we want. This simply tells me that if I take a function in the Schwartz space and take the Fourier transform, I end in the Schwartz space, right. So, this is what we were trying to say. So, to say that f hat is in the Schwartz space, I need to show that any derivative of f hat multiplied by any polynomial is bounded, right. So, what do I have here? I am writing that as some constant which is immaterial times the Fourier transform of some function. What sort of a function is this? I take the function in Schwarz class, multiply by any polynomial, I will still get a Schwarz class function. Differentiate it as many times as I want, I will still get a Schwarz class function. So, this guy is in the Schwarz space. In particular, it is in L1. So, if I take the Fourier transform, I will get a bounded function. So, this guy belongs to Ln, right, which is what we want to show. So, this implies f hat, the original function, is in the Schwarz space. Okay. That is not very surprising because Schwarz space is defined like that, right. You have both the smoothness and the decay built in. So, when I take the Fourier transform, I still get those properties. Okay, but this proves only one way, right. I need to show that if I take something in the Schwarz space, I can write it as the Fourier transform of some other function from the Schwarz space. Okay. So, let us do that. So, let H belong to Schwarz space. Okay. We want to show that there exists some G in the Schwarz space such that G hat equal to F equal to H, right. So, then the image of the Fourier transform will have all Schwarz space functions and that is dense in L2 and we are done. So, take anything in the Schwarz space, we need to find a Schwarz space function whose Fourier transform is this. So, that tells me what is G, right. G should be the inverse Fourier transform of H. Remember, if I have a function f in L1, its Fourier transform in L1, then I can get back f by taking the Fourier, right. So, I can simply get back G by taking the inverse Fourier transform. Okay. So, let us start with that. Define, so we need to prove this. So, define G of x to be 1 by root 2 pi to the n integral over Rn h of t e to the I x dot t dt. Remember, you are taking the inverse Fourier transform, so there is no minus here. Okay. So, it is I x dot t. Ideally, we want h to be g hat. Okay. So, let me repeat, I am taking a function in the Schwarz space, I need to show that there is a g such that g hat is the function we started with. What are we doing? We are inverting h and hoping that that function will work, which means if I take the Fourier transform of g, I should get h, right. This is what we want. Okay. But this definition, just like what we did, tells me that this function, whatever we have defined, is in the Schwarz space, right. So, this is a nice function to start with. Okay. So, G, the way we have defined is a Schwarz class function. So, we can take its Fourier transform, but I want to show that G hat is actually H. Okay. So, let us see how to do that. So, take any, let f be in L1 of Rn, okay, and let us start with integral over Rn with f of x g hat x dx. Okay. Well, what is this? Remember, everything is in L1, some of them are in Schwarz class, all functions are nice. Okay. So, this is nothing but integral over Rn fx. What is g hat x? Well, this is 1 by root 2 pi to the n integral over Rn gy e to the minus iy dot t dy, dot x dy, right. That is the definition of the Fourier transform. So, I am not doing anything highly non-trivial here and I have dx. But now we are in a good position to interchange integrals because f is in L1, g is in L1, right. This is in L1 with respect to y, this is in L1 with respect to x, this gets modulus 1. So, when I take the modulus, you can by Fubini's theorem you can interchange. So, let us interchange. When you interchange, g comes out. So, 1 by root 2 pi to the n integral over Rn gy, okay, I have f e to the minus y dot x dx. That is the definition of the Fourier transform, right? That is f hat at y dy. Okay. Okay. I mean, this is Fubini's theorem. Okay. No highly non-trivial stuff here. Now you do this same thing again. What is G? Well, G has some definition, right? So you plug in this. Right? G has a definition in terms of integral. You plug G here, you have another integral, right? But H is a Schwarzschild function, so it is in L1 with respect to T. This is, so plug in this here. F hat, remember we just proved that if F is in Schwarzschild, F hat is also in Schwarzschild. So this is in L1. Plug in G here. I have two integrals, interchange the integrals. So you will get, what will you get? F hat will become F, this will become H, right? See, it's exactly this, right? Whatever we are doing here because we don't know if G hat is H, right? We are trying to prove G hat is H. If you know G hat is H, then there is nothing here, okay? So I plug in this here, interchange integrals, I will get F and H, okay? So this would be integral over Rn, Ht Ft dt. Okay. Okay, so this is a small trick to prove whatever we want. So now if you look at these two integrals, you see that f is here, f is here. Okay. So I'm integrating g hat, which is a Schwarzschild function, against f. That is same as I am integrating ht, which is a Schwarzschild function, against the same function f, right. So remember one of the exercises, if you look at this, well, you can bring that here, you will get g hat minus h integrated against f is 0, but f was an arbitrary Schwarzschild function, think of it as a CC infinity function and construct an approximate identity. Then you will get that g hat is equal to h, right. So let me write it down, this tells me integral over Rn g hat minus h, right, times f is 0. This is what we know. So replace f with an approximate identity, with an CC infinity approximate identity. Right, because it is true for every f, right. So for every f in Schwarzschild. Okay. So replace it with a CC infinity approximate identity phi sub epsilon. This converges to this guy in L1, right, but it is 0. So this would be 0. So that means g hat is equal to h, which is what we want to prove. So the image has all the Schwarz space functions in L2, and so it is dense, and we are done. Okay. So I'll stop with one or two remarks. So this completes the proof of the Plancherel theorem. But let me emphasize on the definition of the Fourier transform on L2. Okay. So if I take f in L2, what are we doing? We take fn in L1 intersection L2 of Rn, okay, such that let us say fk converges to f in L2, right. Then because it is an isometry and so on, fk hat will converge to something, okay. So converge, so fk hat will be Cauchy, in L2, right, because it is an isometry, right. The norm of fk and norm of fk hat are same. Fk converges to f, so fk is Cauchy in L2, so its Fourier transform will be Cauchy in L2, and so it will converge, right. So hence fk hat converges in L2 to some function, right, to some function g, let us say some function g, okay. So now by definition this g is the Fourier transform of f, right, f hat is g. that is how it is defined. Okay. So, you need to be very careful with manipulating integrals. When you have functions in L1 there is no problem, but if I take a function in L2 I have to choose a sequence. I can choose any sequence, right, it has a unique extension because it is defined on a dense subspace. So, there is no problem. I can choose any sequence which will converge to f in L2 and look at the Fourier transform of those functions, and then that will converge, and that limit is your Fourier transform of f. Okay. So, as a as an example you can take these functions. So, f is in L2 of let us say R. Okay. Look at, consider chi minus R to R f of x. So, this would be in L1 intersection L2 of R, and let us call this f sub R, okay, and f sub R will converge to f in L2. Okay. So, those are all basic measure theoretic assertions, and so if I take the Fourier transform of this it will converge to. So, hence f r hat will converge to f, right, as r goes to infinity, converge to f hat. What is f r hat? So, f r hat at t is simply 1 by root 2 pi integral minus r to r, right. We are restricting the function to minus r to r, f of x e to the minus I x t dx. Okay. So, you can compute, if you can compute this for each r, you can compute f hat as well. Okay. So, this is something which is important, and you should remember how the Fourier transform in L2 is defined. Okay. All right. So, we will stop here.